Today I'm not talking about optics, but more actually scanning internally microscopy. But nevertheless, I want to show you like a collaborative work with Professor Mike Cromie at Berkeley, trying to explore this different solid behavior of electrons using two-dimensional transition metal dichalcogenide. Also, two-dimensional electron gas is arguably the most studied system in physics, but also in engineering, because this is a field effect transistor, like which we have billions in our computers, which really operate by or using a gate to control a two-dimensional electron gas. So if you use a gate voltage, you can attract a lot of electrons. And when you have large enough electron density, basically they become metallic and it becomes highly conducting. And that's how you turn it on. So it is well understood. Then basically, when you have a high density to the electron gas, you basically form a metallic Landau Fermi liquid. However, it was also known a long time ago that if the electron density is very low, they will actually not be in the liquid phase, but instead they will actually form a two-dimensional electron solid known as Wigner crystal. Or the way to understand Wigner crystal, actually, I learned from Andy when I was a graduate student at Columbia. So it's really controlled by the parameter Rs, which defines the computation between kinetic energy of electron and potential energy of electron. So when the kinetic energy is high, or when, which means that when Rs is small, then the electrons just want to lower its kinetic energy by being very delocalized. On the other hand, when the potential energy is very large, or it basically wants to minimize the potential energy and then basically to stay apart from each other, and they form this Wigner crystal phase. Quantitatively, the potential energy scales with E squared over A modified by dielectric constant. And then A is basically characteristic distance between electrons. And the kinetic energy scales with P squared over 2m. So it scales with 1 over A squared. So it's easy to show that Rs has this expression. So it basically is proportional to effective mass of electrons. So if you want to have strong correlation on large Rs, it's good to have large electron density. And furthermore, it scales with the distance between electrons, which is square root of n. So basically, when you want to have strong correlation, you want, or want to push to the Wigner crystal phase, you want large effective mass and large electron separation or low density. And although this general idea is very well understood. So at high density, you have a liquid. At low density, you have a solid. But there are actually still a lot of outstanding questions regarding the electron solid or like the Wigner crystal. Or one is like, how does the melting happen when you go from the Fermi liquid case to the Wigner crystal solid? And the other thing is, so for experimentalists, unavoidably, there are disorders in real materials. So how does disorder affect this kind of a liquid-solid transition and the general behavior of the Wigner crystal electron solid? And furthermore, in addition to have random disorders with two-dimensional material, we can actually controllably create potential fluctuations. So now with this kind of well-defined potential confinement, how would this electron solid behavior change? So these are all questions that one can explore by using two-dimensional van der Waals materials, because now we can exfoliate individual layers of 2D semiconductors, and we can stack them in many different ways. So as a result, a simplest case is if you have a simple semiconductor 2D layer, basically you have you can create a plane to the electron gas, and naturally you'll find there are quite a few disorders around, so you can study the disorder effect on the Wigner crystal. But furthermore, by combining heterostructures, sometimes you can create one-dimensional periodical potential This is an example of these 1D domain walls, and you can even form an array of them. And also, it's very well known by having twisted samples, you can form a two-dimensional periodical potential. So one can ask, or when you have this 1D periodical potential and 2D periodical potential, how would this electron solid behavior change or look like? So today I will tell you our efforts trying to kind of explore in those directions. So first I will consider the situation of 2D Moire superlattice. And when you add many electrons in the system, how Wigner molecule type of states can emerge, which they form a periodical array themselves. And then I will tell you what happens when you have these 1D domain walls, either in individual 1D domain wall where you can see Luttinger liquid behavior, or arrays of domain walls where you can actually see coupling between adjacent 1D chains. And last, I will show you what happens when you have just plain 2D material, but with disorder, how the Wigner solid and this kind of solid liquid transition look like. Okay, so we start with the first case where you have Moire superlattices. Many of you might have seen these pictures, like when you have 2D material, either they have a small lattice mismatch, or if you add a twist angle, then the two-layer lattice constant has a small difference, and that create a long-range periodical potential that the electron can see. And when you dope electron in this Moire superlattice, you can realize a Hubbard model where you can get all kind of correlated insulator and topological states, and even superconductivity when you have doped multi-insulators. But most of those studies focus on the situation where you have one electron or like a fraction of electron per Moire unit cell. What we would like to explore mostly here is actually when you have a Moire potential that's very deep, and when you can put many electrons in a single Moire unit cell, what will happen? So imagine that all the Moire potential is very deep in a single unit cell. You can approximate it as basically a deep harmonic oscillator. And for individual unit cell, you can think it's like an artificial atom where you add electrons into it. So when you add multiple electrons in a kind of a quantum dot or like an artificial atom, there are actually, again, two competition between kinetic energy and potential energy. So kinetic energy, you can think basically is these quantized levels of individual electrons. And then the potential energy is a Coulomb potential. And depend on the competition, the feeding of electron can happen in two different ways. One is if this quantization energy is larger than basically the Coulomb interaction, or then we'll just feel things like one by one. So you basically, the lowest state, you have feel 2 electrons, and then another 2 electrons feel at this higher state, and so on and so forth. On the other hand, when the Coulomb interaction is very large, then it will just neglect all these quantized levels. So again, electrons won't just be far apart from each other. So then basically, they can just be pushed away from the center. So although the center has the lowest potential, but when the Coulomb potential dominates, that can actually correspond to lowest electron density. So in Moire superlattice, it turns out that this kind of a competition between our Coulomb energy U and this quantized energy delta can be tuned in different systems and tuned by a Moire period. So one can actually indeed push them into different limits. So in order to see this electron lattice, we will mostly use scanning tunneling microscopy because it has very high spatial resolution. And in order to create this model system where we want a very deep potential so that it can hold many, many electrons or holes, we will mostly use this near 60-degree twisted bilayer WS2. So basically, our theoretical collaborator, Professor Steve Lewis' group tells us this system has a particularly strong moire potential, partly due to two reasons. One is, in general, homo bilayer tends to give you stronger hybridization compared with hetero bilayer. So you want to basically have two TMD layers of the same type. And also for WS2, it turns out, or especially for the whole band, when the two layer hybridize, it turns a gamma point actually becomes the lowest energy state for the valence band rather than K point. And it has been shown that the gamma point tends to have much stronger hybridization, and that helps to give a very strong kind of a potential confinement. And or 60-degree twist angle also helps. I mean, it turns out the lattice reconstruction create a strain pattern that further helps. So all these things added together give a very deep potential well for this system. Okay, so once we have electron in it, and if we want to image this kind of electron solid state, there is actually a subtlety about doing scanning tunneling microscopy that we need to pay attention of. So if we, because if you want to image, say, the Wigner crystal electron solid, you want to make sure that the tip is probing the electron density, but doesn't perturb the system too much. But if you do a conventional scanning tunneling microscopy, what people usually, which is well developed in studying metallic state, is usually you will use a very small tip bias between the tip and the sample, and then you probe low energy physics, and basically the DI/dV curve tells you the effective density of state. However, this kind of picture or this probe doesn't work very well for semiconductors or 2D semiconductors. And the reason is because if you have a doped semiconductor, say here is an n-doped semiconductor, the work function of the semiconductor and the work function of the metal tends to be very different by hundreds of millieV or sometimes 1 electron volt. So that's why if you have a metal and a semiconductor, they usually form a well-known Schottky barrier. So in this case, if you have a small tip bias, then what happens is basically, or since if you apply small bias, then the work function has to align. Then because they have very different, the first work function, the electrochemical potential has to align. And then because they have very different work function, then the basically vacuum level will be very strongly offset. So that means basically there will be a very strong band bending, and there will be a very large electric field between the STM tip and the sample, which creates the band bending in semiconductor physics, like the Schottky barriers. And this means this very large electric field below your tip basically will push the electrons around and strongly perturb the system. So you will not be able to get a simple like density of state mapping, or you will not be able to map out electron density because everything is kind of perturbed or destroyed by the tip itself. So in order to overcome this difficulty, what we can do is actually purposely apply a relatively large bias voltage between the sample and the tip. So the idea is we will use the bias voltage to compensate the work function difference. So in this case, the electrochemical potential between the Fermi energy between the semiconductor and then the tip is very different. There is a very large Fermi energy difference controlled by the bias voltage. But then when you apply, when this difference basically compensates the work function difference, you can see the vacuum level actually aligns. That means there is no net electrical potential between the tip and the sample. You don't have residue building electric field. So in this case, the tip will provide minimum perturbation to your electron system. But at the same time, because the Fermi energy is very different, then the doped electron in the conduction band of the semiconductor will still be able to tunnel into the tip and give you a finite tunneling current. So in this case, we call it, and basically this tunneling current only comes from conduction band edge state. So in this case, basically, if you measure not the IDV, but on the net tunneling current, the tunneling current will actually tell you what's the local electron density in the conduction band that can tunnel into the tip. Or similar scheme can be used for whole doped sample. Again, you basically apply bias voltage that you compensate the work function difference, and then the holes can tunnel into the tip. So in this case, by measuring the kind of tunneling current itself, you would be able to know what's the local electron or hole density. So here, just showing some experimental result related to this tunneling behavior. So the left part shows basically, this is actually a DIDV curve as a function, or maybe a tunneling current, as a function of the bias voltage between the tip and the sample, as well as the vertical axis is the gate voltage. So what we can see is when we put the tip is a little bit far away from the sample, and then just vary the bias voltage, we can see basically a tunneling current in this side, on that side, and there's a relatively large gap in the middle. So this is very similar to a conventional situation. You can tunnel into the conduction band and valence band, but when the tip chemical potential is inside the gap, you see very little tunneling current. But when we actually push the tip very close to the sample, we actually found that, or if we zoom in the kind of close to the gap region, we actually found that there is a finite tunneling current even inside the gap, which corresponds to this situation. So even when the tip kind of a Fermi energy is inside the gap, as long as you have doped sample, there is actually a finite tunneling current. And then that tunneling current will be able to tell us what's the local electron density distribution. So with this method, we can start to kind of or look at the electron or hole distribution in the system. So we'll first look at the hole doped case, where you have or basically apply a negative gate voltage on the bilayer WS2, and then you start to dope hole in the system. So this is where, yes.
Can we just go back a slide?
Yes.
And help me on 2 points. So the first is that, yeah, as you say, the usual discussion is that the WSE2 is hole doped. So we put electrons in, we take out electrons from the top of the valence band of WSE2, right? And that's where the discussion of Wigner crystals and TMDCs and so on come from. Are you really interested in the case where the WS2 is electron doped and it's those electrons that are forming the Wigner crystal?
In principle, we can study both sides.
Right, but which one are we talking about here? I'm just confused because
we'll do both.
But a lot of your discussion here has to do with using as your probe electrons in the conduction band. And I thought that in many cases, like your one hole dope, you don't have any electrons in the conduction band.
Okay. So yeah, so there are two pictures here. So in this case, we'll probe the electron in conduction band. And then we can also gate it to hole dope. Then we can also probe hole in the valence band. So we can do both. And I will show you results for both electrons and holes.
And then my other question is just for theoretical background. What does the theory collaborators tell you about the size and shape and depth of the potential wells that we're talking about here?
So for hetero bilayers, like for the WS2, I think they can be like 300 or 400 millieV deep. The width is basically determined by the moire.
I understand, but in practice for things like this, how?
It's around 10 nanometer is the one that we will be mostly looking at, around 10 nanometer. Yeah.
And how many? So that means that if I just taking into account the Coulomb energy of a couple of electrons in that, it sounds like this is in a case where U is less than the depth of the well. If I do E squared over epsilon.
Yeah, U is definitely less than the depth of the well, but it's larger or comparable. I mean, it's definitely, it's actually larger than the
level spacing
harmonic
inside
level spacing. That's right. Yes, yes. So I mean, yeah, U is definitely smaller than depth of the well. That's why you can put multiple carriers in one well. Right?
Okay, thanks. Sorry.
Oh yes.
So maybe one question on, so the sample you are considering here is gamma valley or K valley? So when you hold up, you're injecting holes in the gamma valley or the
Yeah, so since I'm talking about a few different systems, so they will vary. Like for the holes, is actually or in gamma valley. For the electrons, there's some uncertainty, but now we think it's most likely to be in the K valley for the electrons. Okay, so this is the holes, and then this potential is very deep and is in the gamma valley. So when we put one hole per moire superlattice, so basically you actually see these holes are indeed localized nicely in this periodical moire superlattice. But when you start to add two holes per moire superlattice, or you can see in the non-interacting picture, or two particles can sit in the same electronic state. But we can already see the charge distribution is quite a bit different. It is certainly spread out, and there is also kind of a dip in the middle. When we have three holes per moire superlattice, you can see very dramatic change, where now they really avoid the center position, and they form actually a triangle for three holes. When you have four holes, they have all kind of a triangle, but then some kind of blurring thing in the middle. We can qualitatively understood this behavior, just still think about individual moire superlattice first, just think it as a quantum dot. When you have two hole per superlattice, because of the triangle lattice, the potential is kind of somewhat triangle shaped. And then there are basically three equivalent configuration in the classical picture when you want to just minimize the classical potential energy. But then quantum mechanically, all these states will hybridize. So they theory actually predict you will form really like a donut shape. But in the real system, what happens is there's also a small residue strain. So we don't see a perfect donut shape. It's like a little bit elongated in that direction, but you can clearly see a dip in the middle. So when you have three hole per lattice side, then this classical configuration really dominates. There's only a single classical configuration to minimize the potential energy, and that's basically the situation will look like. When you have four holes, so what happens? Hand wavingly, you can think three holes want to be very far apart from each other, but then the last one doesn't have any way to go, so it basically becomes more delocalized. So we can also look at what happens on the electron side. For the electron side, we think the electron is likely to be at the K doping, so the potential will be not as strong. We basically find that one electron is like this, and two electrons spread out a little bit, and three electrons also show a triangle-like thing, but it's not as obvious as the whole side. So the difference is basically the effective mass as well as the kind of moire potential are slightly different between the electron and the whole side. Yes?
Yeah, maybe what about incommensurate filling factors? Like instead of having commensurate filling factors of the molecule itself, what happens when you?
So it's a part of partial field rather than
full.
Yeah. So when it's a partially filled case, for example, if you have one electron and two electrons, then you will see. So it's kind of some position will be like filled with one electron, and some position will look like two electrons, and they form like something like those generalized Wigner crystal configuration where the like a two-hole Palladius site will avoid the nearest neighbor, you actually have those kind of patterns start off.
So generically, is always like incompressible the state that you find?
So that's a very good question. So if it's, I mean, for the intermediate feeling, like if it's not, say, 1.5, so it's more like a really incommensurate, it's hard to, I mean, in transport, maybe there will be some compressible state, but it's very hard for STM to tell. Like yeah, with STM, you only look at the kind of a localized configuration, and very often we still see like a fairly well defined, like 1 or 2 occupation at a different position.
Yes, you see some form of phase separation. Is that
so when in the region that is relatively homogeneous, we don't really see phase separation, but we more see like just again, if you think about when you want to minimize the potential energy, like the 2 electron occupied, which has larger charge, they will actually want to be further apart from each other. So you don't actually see phase separation. Instead, you will see this 1 electron, 2 electron distribution will be more kind of spread out between them.
Begs the question about the shape of the potential. How does it change between the electron side and the hole side?
So I think they actually localize a different part of the Moire unit cell, and so for electron side, it's definitely less steep.
And the shape, like, is it like a triangle lattice or is it honeycomb lattice? The bottom.
Oh, they are all kind of they are all triangle lattices for this 60-degree twisted samples.
Both the electron and the hole side.
Yeah, for both electron side and the hole side. Like so that's the thing. So if you are close to 0 twist angle, you tend to have for homo bilayer, you tend to have hexagonal lattices. But for close to 60-degree angle, you usually get triangle lattices. Yes.
Are there regimes where the molecular orientation can show a correlation, or is it always the potential? Like this 3-electron case, they might be somewhat turned. Is that just?
Yeah. So maybe I will show you in the next. Yeah, so I think that's largely determined by the kind of accidental strain in the situation. Okay, so here I just show you like, when you change the Moire period a little bit, then so when the Moire period is a little bit large, you can see the pretty well-defined 3 dot. And when the Moire period is smaller, then it's kind of harder to distinguish. So maybe when you change the Moire period, this competition between potential and kinetic energy is a little bit different. And furthermore, in a lot of systems, there are random strains. Like and when you have strain, the kind of configuration can change very dramatically. And yeah, the thing that you see a little bit anisotropic, I think, is largely due to there's some residue strain, and then the strain basically will distort the kind of nearby region or in similar ways. So yeah, I guess it will be a very interesting question to ask, like if you have really kind of or no strain, whether there will be some spontaneously like pneumatic type of order come up. So I think we haven't been able to distinguish that yet.
Because the intermolecular interaction should still be pretty strong, right? The scale.
Yeah, that's right. Indeed, yes.
So this was exactly also my question. So as far as understood, the Wigner crystallization is something coming from the long-range Coulomb interaction, right? If I understand your model or your understanding of the system here so far correctly, you basically trap electrons in deep potentials due to the Moire potential, right?
Yeah. So first, I mean, maybe the terminology of Wigner molecule is what people have used when they study actually the quantum dot. So inside of a quantum dot, in a single quantum dot, when you have multiple electrons, they form this. I mean, so it's still, I mean, the long range is relative. So this is basically still the way in a single quantum dot, they form these separated electrons dominated by Coulomb interaction was historically called Wigner molecules. And then basically we just have, so in this case, we just think this is a periodical array of this quantum dot. So the energy is dominated by individual quantum dot, but indeed there should be some coupling between adjacent quantum dot and hopping, and those will be things that will be interesting to learn in the future. Okay, any other questions? Okay, so now let's go beyond the quantum dot, which is largely a kind of a 0D case where you have multiple electrons. Let's go to 1D case when you add many electrons. So if you have 2D material together, and imagine they are perfectly aligned, but you just stretch one relative to the other a little bit, then basically, or from one side, the atom may be kind of aligned, and then after some distance, it will be shifted by one atom. And because the material would prefer the AB or BA type of stacking, then they will reconstruct and push all the strain inside a narrow, relatively narrow region, basically form a domain wall. So when they concentrate this strain, basically there is a lattice registration shift of one atom, basically in this relatively narrow region. And then they basically can form these layer stacking domain walls. Or you can imagine if you have a very little strain, they will concentrate it in one or a very few domain walls. But when the strain is relatively large, it will actually be able to realize kind of a periodical array of these domain walls. So basically each domain wall will give you one lattice shift. And if you have many lattice shifts, they basically will form this periodical array of domain walls. So these one-dimensional domain wall then actually provide a very nice system to explore kind of Luttinger liquid or 1D physics, because they are compared with what people have done in other 1D systems, they actually have several unique advantages. Like, or compared with what people can do with quantum wires, this domain wall is actually very strong confinement. The lateral dimension is only about 1 nanometer, so it's really in the 1D limit. And compared with carbon nanotube, this also has advantage in the sense they can actually be made much cleaner. So if you have, or ideal nanotube is very clean, but once you start to make like device out of it or like fabrication, they tend to be a lot of sorbate, and basically kind of those disorders dominate almost everything that you want to measure. But in this case, or make use of all these things we have learned about this exfoliation and stacking, we can actually keep the system rather clean, and also because these 1D domain wall are embedded in a 2D system. So when you make electrical contacts and make electrical devices, it's much more straightforward and basically allow us to control the doping and do all kind of measurement much more conveniently. Okay, so this is a case when we start to dope electrons in an individual domain wall. So in this case, again, in most materials, there are naturally defects. And in this case, the defect, there are two defects over here. So they basically form pinning center. Those charge doesn't move. And when you add the electron in the system, you can see basically when you increase the electron density, they just form this kind of electron necklace. So this basically can be considered as a 1D Wigner crystal. We know in strict 1D, there's no long range order, but in a finite chain, they look as good as a crystal that you can think of. And then when you start to increase the electron density, then this Wigner crystal basically will start to deform, and they start to kind of melt. So here is the intermediate electron density level. So at the lower density side, you still see the very nice periodical density of electron. At the higher density is actually, the oscillation becomes harder to see. But in order to increase the signal to noise ratio, what we can do is just integrate along this vertical direction, and then also just change the kind of zoom in the amplitude change, then what we can see is like across this density change, there are still kind of oscillation that's present. And furthermore, we actually see something interesting, like at the bottom part, you see this almost periodic Wigner crystal period. And when you increase the electron density, there's actually a dimerization behavior. So what you can see is these two lines, when they go up, they actually get closer to each other. And this is kind of confirmed by DMRG simulations. So you can actually see that indeed, when you increase the electron density, there will be a kind of electron dimerization. There are different ways to understand this dimerization behavior. Like some theories say, oh, these are all described by just interacting Luttinger liquid when you vary the density. But for physics, experimentalists, I would like to see whether there are some more intuitive physical picture that can kind of describe this phenomena. And there was a theoretical paper early on actually talk about when the how this dimerization can appear. So what they argue is that in the Wigner crystal region, basically the electron actually has antiferromagnetic coupling. So when the density becomes a little bit higher, the antiferromagnetic coupling actually or increase kind of exponentially. So it increase. So when this antiferromagnetic coupling becomes large enough, then what you can see is there's a competition between the Coulomb potential, where they just want the electron to form a perfect lattice, and this antiferromagnetic coupling, they want to form kind of singlet pairs. So the competition of this elastic energy and the magnetic energy basically can drive a dimerization behavior. And this can be kind of confirmed by the DMRG calculation. So if we look at this dimerized part and we calculate the spin correlation between the adjacent electrons, we see that indeed in the kind of a dimerized part, the kind of spin singlet antiferromagnetic coupling of the spin is enhanced. So in that sense, this is actually analogous to the dimerization in the polyacetylene. Like it basically want to basically dimerize to lower kind of some kind of basically spin singlet energy. So, and then if we go to even higher density, then basically the oscillation, the dimerization thing basically is not obvious anymore. So we really just see like reduced oscillation period at 1/2 of the this case. A period that is like doubled or k. The k is 1/2. So if we do basically a Fourier transform, what we can see is at the low density, the Wigner crystal, when you have like spin half system, it has an oscillation period of 4kF. And then when the or the density is very high, it's basically like weakly interacting Luttinger liquid, you have only the 2kF oscillation. And in the intermediate region where you see strong 2kF and 4kF component is where the dimerization behavior is the strongest.
Is it feasible to do these experiments in magnetic field? Because according to this story, the dimerization is associated with singlet. So if I just polarize everybody, it should go away.
It is feasible, and Professor Cromie is trying to do it. It does need a pretty strong magnetic field. So the STM that we did this work does not have a magnetic field, but there is a system that in Mike's group that they have a magnetic field. So, and that's what we are indeed trying. Right?
Help you enough. All right, interesting.
And also a quick question about the experimental realization. Do you need to be lucky to find defects, or can you put defects where you want and engineer these pinning on your own?
right now it is. I mean, these defects are naturally present. We just use it. But yeah, but create a defect is actually quite possible with STM. We can just zap it with a high current. Then we can indeed. It's hard to make defect go away, but to create a new defect is quite doable. Actually. Okay, then we can study what happens when you have these arrays of like 1D channels. So basically, well, we can first look at the very low density limit, where you can see here individual 1D domain will actually form basically a Wigner crystal state. But then when you look at the adjacent ones, you see this electron really form this zigzag pattern. And when you do a 2D Fourier transform, you can see actually very nice diffraction pattern. So this basically says that in the low density limit, the coupling between the chains are strong enough. They basically form, and then again, to minimize the Coulomb energy, the electrons want to be far apart from each other. That's why they form these like zigzag chains. And they basically stabilize like a two-dimensional electron crystal. However, in this case, when we change the electron density, the chain-chain interaction strength actually can be modulated. The way to understand this is actually fairly straightforward. If you have a periodical charge in one chain, and you ask in the adjacent chain, what's the kind of or residue periodical potential. So when you increase the electron density or the DC energy, suddenly the net Coulomb potential suddenly increase. But if you look at the periodical oscillation part, you'll find that the periodical oscillation part actually will decrease exponentially when the chain separation is larger than this two particle separation. So this is just simple electrostatics. So what you can see is when the kind of a chain-chain separation becomes larger than electron-electron separation, the kind of the coupling constant decrease very strongly. And then we can easily change the electron density. And when the density becomes high, the electron distance becomes small. Then it turns out that the periodical coupling between the chain becomes weaker. So in this case, what we found is like when we go to or higher and or even higher densities, what we can see is inside individual chain, you still have Wigner crystallization. So you have order along that direction. But between different chains, then they don't have any phase coherence anymore. So it's kind of a random phase. So what happens basically, and if you do a diffraction pattern again, so you can see in this case, they are well kind of crystallized. But in this case, you can see along this this direction. So you have a well-defined point here, but along this direction, they are very much spread out. So that means there is really no kind of a correlation, phase correlation between the different chains. And that's just because, so this actually, the random phase difference between different chains here is actually driven by disorders, because each line has slightly different random disorder. So when the chain-chain interaction is very strong, the electron lattice will actually stretch to make them to basically have exactly the same period and form an ordered behavior. But when the chain-chain interaction is very weak, they just don't care. So they basically each have a random phase. So in this case, you have order along one direction and disorder along the other direction. So it kind of is analogous to this symmetric liquid crystal phase. They have basically order along one direction, but disorder along the other direction. So you can think this as an example of a symmetric, like an electron liquid crystal, basically at this situation. Okay, so last we'll go back to the supposedly the simplest case where you don't have any periodical potential in the system. So basically, so if we have only a simple 2D system, when we dope the electron, what's the original Wigner crystal will look like? So in order to kind of study the Wigner crystal phase, we think, I mean, we are motivated to look at system with large effective mass of the charge carriers, because the simple analysis tells us if you have large effective mass, basically you have like a large RS, and then the Wigner crystals phase can be more robust. And with transition metal dicoordinate, we actually have different choices. We can have different monolayer transition metal dicoordinate. We can also have different, say, bilayer, trilayers, and so on and so forth. And here I actually show a kind of an initial calculation of MOSE2 for monolayer, bilayer, and trilayer, and look at the effective mass for holes. So what we found, if you have a monolayer MOSE2, the K-value electron has a mass of about 0.5, but then the gamma value actually has very large effective mass for holes. However, for monolayer, the gamma value is very deep. So like when you dope holes, it's not accessible, so it's not very useful. However, if you look at the bilayer MOSE2, due to the layer hybridization, it turns out the gamma point actually becomes the lowest energy state. So when you dope holes, you can now access the gamma point. And then the theory calculation shows the effective mass of the gamma point holes still is quite large, more than 1. So as a result, it motivated us to actually study not monolayer MOSE2, but bilayer MOSE2. And for hole doping side, we can use this large effective mass so that then the kind of or electron solid can exist in a higher like density range. So this basically is the experimental data for a hole doped MOSE2 sample. So the left-hand side image shows just the topography image. So now we found that this sample actually is not the best sample. Like the disorder is relatively high. Like so, you can see these bright points. So those are kind of charged disorders that are particularly strong in the topography image. But if you
You know what they are?
I mean, are they vacancies? Are they oxygen instead of sulfur? Are they something instead of tungsten?
Actually, for the charged defect, I think there's still no consensus what they are. So we also see there are actually even more weaker disorders that, so like this point, if you kind of, so some of those are oxygen replacing sulfur. So basically this substitution is a isovalent defect. So they are not charge defect. And some people claim even for the vacancy, they actually behave more like a isovalent defect. So I think people are still trying to figure out exactly what defects are there. But the oxygen replacing sulfur or selenide seems to be a common thing that are present. Okay, and then if we start to kind of a dope hole in the system, so what we can see is all these charge density are rather localized. They are very spotty. So that kind of led us to think these are more like a solid behavior. The electrons are really rather well localized at specific point rather than like electron liquid where they are more spread out and homogeneous. And if we kind of look at the individual region, some of them can be semi like a triangle lattice. But what you can clearly see is like or the orientation of these are kind of random. So this doesn't have long range order at all. So they are kind of a disordered electron solid. So if we kind of are trying to determine the position of individual dot using some kind of a mathematical treatment, we can then identify or what are the individual particle and how many nearest neighbor they have. So in an ideal situation, basically every single atom should have 6 nearest neighbors. But with this disorder, what we found is about 60% of the holes have 6 nearest neighbors, and then there are about 40 of them has 5 or 7 membered like nearest neighbors. So that means indeed the disorder is rather strong. These pentagon and the heptagon cells are very common. And then what we can do is basically change the electron density and study how basically the solid behavior change, and also at the end at very high density, how do they melt? So, okay, maybe just one comment. So this actually is already at 5 × 10⁻¹² centimeters square. So this is already a very rather high density. If you think about gallium arsenide, usually the Wigner crystal is present at electron density like 10⁻⁻10 or even less. So this is actually several times 10⁻12. So it's really benefit from the very strong Coulomb interactions because the dielectric constant is smaller, and also the effective mass is very large. Okay. So we can study actually how the electron density change both in the solid phase as well as the solid liquid kind of a transition. So firstly, if we just zoom in a small region and see like the whole thing is like solid, but when we just increase the electron density, how does the solid evolve? So in the ideal Wigner crystal, the picture is actually pretty straightforward. When you increase the density, everything will just shrink homogeneously. But now with the disorder, the situation is rather different and maybe a little bit also interesting. So because there are some points that are fixed, so you cannot have a homogeneous kind of a change. So what really happens is you kind of need to squeeze the electrons to form like a interstitial or like defects in the local solid. So one thing, for example, initially you can see there are like 4 electrons in this dashed box. When you start to increase the electron density, what you can see is actually they are start to have some kind of fuzziness around these electrons. And when the electron density is further increased, it basically forms this 5 electron over here. And similarly, if you want to further increase the electron density, then basically it becomes fuzzier, and then it becomes a more well-defined 6 particle state here. So it's like you are adding quantum defect into this local region. That's how this like density increase in this solid region. And then next we can just go to even higher density and see how things melt. Like so in this case, all things are mostly spotty, it's like a solid. And when we increase the electron density, what we found is in some region, it becomes more or less homogeneous. So I mean, it's hard to have a perfect probe for solid and liquid. So the kind of for experimental purpose, we just say, or look at the local contrast. If the kind of percentage contrast change is very small, we say that's almost like a liquid phase. And if the contrast is very strong, then we say it's like a solid phase. So you use that kind of kind of a practical criteria. We can see that when we increase the density, first there are kind of small bubble region where the kind of liquid phase emerge. And when you increase the density, they kind of expand. And when you increase the density more, they kind of start to form a percolation pathway. So it's like maybe the solid to liquid change, at least with this disordered system, is like a percolation, like formation process. But then there is certainly a pretty large density range. You basically have mixture of liquid and solid behavior. Okay, this kind of electron liquid solid mixture phase can potentially have many different physical origins. Two commonly described the picture is a scenario like this. One scenario is like once you have disorder, maybe a natural thing to have is if you have long-range potential fluctuation, then when you increase the electron density, some region will have higher density, some region will have lower density. Then naturally, lower density part will be more like solid, and higher density part will be more like liquid. And this long-range potential disorder can naturally lead to a liquid-solid mixture. There's also some theoretical proposal arguing that the electron and solid region will happen even spontaneously in an ideal electron solid without disorder. But then with disorder, maybe then this electron solid phase can be further localized and kind of, or maybe even stabilized a little bit. So what we can do is we can actually at least test the scenario 1 to see whether this higher density, I mean, the liquid and solid phase is correlated with long-range potential fluctuation. So the argument is like this: like if you have a long-range potential fluctuation coming from the disorder, so that will be basically a fixed pattern. So that will be present both for low electron density and high electron density. So if at the low electron density limit, we actually have the electron solid, we can really count the local electrons and then know what's the local electron density. And we can have this electron density map. So locally, we see large fluctuations, but we don't see long range, basically, variation of electron density average. And in particular, if we look at this later, the region that later become liquid versus the region that actually will remain solid, and compare with the average, the electron density, we found there's no correlation at all. So that means it's really not driven by a long range potential fluctuation. It's more like, but we do see the solid region is kind of correlated with higher defect densities. So I think what happens is defects still play a very important role. They are definitely pinning the solid. They might also kind of make the solid more stable across a larger electron density. But yeah, further understanding, I guess, requires more theoretical work. Okay, with that, I would like to conclude. So with this 2D system, when you have 2D potential, 1D potential, or even without potential, the electron solid behavior can actually manifest in very different ways, and there will be many more studies may be needed to fully understand their behavior. And I would like to thank people who, so this is a very strong collaboration with Mike Cromie's group at Berkeley. So the experimental work is really spearheaded by a talented graduate student, Hongyuan Li, and with help from Ziyu and Jiang Han. And the theory work of initial calculation by meeting Louis' group, and the 1D case coming from Tianle in Zeratel group, and then Wigner molecule coming from Liang Fu's group. And we also have discussion with Steve Kivelson and the sample coming from the Arizona State, and BN coming from Japan. And thank you for your attention.
For the second part, the last part of your talk, you said, okay, the bilayer has the wonderful optimal, let's say, effective mass in the gamma valley. But there you also have this bonding anti-bonding formation. You said it before, so there the hybridization between the layers is also the strongest, right? In the gamma valley. Meaning, I think you're doping into something like an anti-bonding state between the two layers, which might be the reason why this might be more strongly affected by the impurities, since both layers might act on the same state. Anyway, what I wanted to ask is, did you try the same also for the mono layer? Even though in the K valley the effective mass is not optimal, but there you might get more clean scenarios. I wonder if you might get more clean scenarios.
Yeah. So we are trying more samples in different monolayers, bilayers, and improve the defect densities. One problem with STM is a very slow measurement compared with many transport or even optical thing. Like for each sample, require many months. So we haven't systematically compared the different system yet. Yeah, but we are actually. So mostly still focusing on bilayer, but looking at more like sources coming from different places to see whether we can get the higher quality sample with lower defects. Like,
So quick question about the metallic gate that you have to control the doping. How far is it from the sample? Are you worried about the screening effect of that gate?
Yeah, that's a very good question. So, so right now, these samples, the gate are still like maybe 20 nanometer away. Given the electron density over here, I mean, the electron-electron separation are all 10 nanometer or smaller. So we think the gate effect is relatively small. It's not very strong.
Not negligible. That's cool. Okay.
But yeah, in the future, or once we have a good handle on this, it will be good to have even thinner BN, so you have stronger screening effect and see basically to really quantitative study what their effects are. So I think right now they are relatively weak, but maybe you can say they are still present.
Here's if you had a comparison with the classical transition, and if you have the actual signatures of some quantum fluctuations in this node. Find some way.
That's a very good question. So maybe we can have more discussion. I actually don't know what will be the signature. I guess I mean, in the solid case, when we add the electrons, the way that it behaves seems to be at least kind of quantum, like in the sense you have delocalized electrons. In this transition, I don't know what are the signature to look at. So
I think it should be something beyond percolation. I think quantum tunneling will address it beyond percolation is usually the picture.
Okay. Yeah. So
signatures in that maybe I don't know. Probably very hard to go patch to patch because that's a big scan. But
that's right. So I guess
it should be very interesting to think about. I don't know. Yeah.
Yeah, maybe we can discuss more to see like what kind. Yeah, I think it requires basically targeted measurement with very fine kind of.
So, two questions about this. Do you have an experimental way of assessing the density in the ordered and disordered patches? I mean, I can sort of imagine you can count the localized electrons. But in the patches which you identify as metallic and liquid, is there an experimental way to know what the local density is?
It's harder. That's a very good question. Like, so I mean, although these are rather smooth, if we do Fourier transform, they are still like a vague kind of a pattern that we can see. Maybe we can try to correlate that with, I mean, say Fermi energy or something to compare it with electron density. But I don't know how quantitative. I mean, it's pretty fuzzy, so I don't know how quantitative we can get in that case. Beyond that,
I guess the question is, can I interpret the STM spectra as a density of states and just integrate them over some range and compare the integral?
Okay, I can think about, yeah, so that basically you need to assume the tunneling probability like is a constant or something.
Yeah,
like
there's all of these, but if the energy scales aren't that big, you know, usually tunneling probability, but anyway. Okay, the reason why I ask is that there's two reasons to have this metallic fluid. One is the Kivelson reason, which is more or less managing charge density. And the other is just you have two phases. There's a first order transition between them. One is spin by disorder, one isn't. So even at the same density, you can have locally stable, both metallic and Wigner crystal ordered phases. So that's why it's interesting to know how big the densities are, to know whether the mechanism for this is a density and homogeneity or something else. My second question, which pertains both to this and to your array of one-dimensional guys, was did you do Moire-like constructions and things like that, right? There's ways to assess how much actual long-range order you have by, you know, how many defects there are in the Wigner crystal by doing things like drawing loops and counting angles and so on.
Yeah, so that's what we actually did. Like for the, I mean, 1D array, they actually shows pretty nice behavior. Like, I mean, the range is, I mean, the scanning range is not very large, but at least in the range that you have, I mean, given the diffraction pattern is very sharp, that's.
You know, the diffraction pattern is fine, but identify there are standard constructions right, that allow you to identify defects and density of defects and correlation lengths and things like that.
Okay, yeah, I guess maybe just the scanning range. I mean, the sample range is not large enough to get a long range one, but for the 2D case, yeah, we don't see. I mean, we can see that it's rather disordered locally,
Right.
so there is no long range order. So we did
I guess the question was, it interesting to look for the densities of defects and you know, density of disclinations and dislocations. But all right, we can discuss that offline.
Okay, yeah. To know what to do next will be very helpful.